we can use that definition that the sequence, so that the limit has to be fulfilled for every sequence to prove that the given function doesn't have a limit. Okay, so if I give you this sequence, the sine of pi divided by x, and we want to compute the limit when x goes to 0 of the sine of pi over x. Okay, what's this? Right? So the domain of this function is again the reals minus 0, right? Because when x is 0, the fraction does not exist. And now we want to know what happens to this limit, right? So the idea, if you think about the sequence, right, sine of 1 over n, sorry, sine of, if x goes to 0, right, this is like, and this is pi over x, this is like approaching infinity, right? Because when x gets small, this argument gets very large. But we know that the sine doesn't have a limit when x goes to infinity, right? Or when n, you think about the sequences. It's always alternating, okay? So this is not going to have a limit, and we can prove it, okay? So let's suppose we take a sequence. X sub n is 1 over n, right? So now f of x sub n is the sine of n times pi, right? Now the sine of n times pi is 0, right? For all n. So you could think that the limit of f when n goes to infinity is going to be 0, right? But we can take another sequence, y sub n, and let's write it like this. 2 over 4n plus 1, okay? And you'll see now why I've chosen this one. This is the sine of pi divided by this, and this is equal to pi times 2n plus 1 half, okay? This is 1 over y sub n. And these are all the points at which the sine is valued 1, right? And you can actually expand this. This is equal to 2 pi n plus pi over 2, and you can expand this. Uses the sine of the sum formula, so this is equal to the sine of 2 pi n times the cosine of pi over 2 plus the sine of pi over 2 times the cosine of 2 pi n. Now the sine of 2 pi n, we know it's 0, the cosine of 2 pi n is 1, so this is equal to the sine of pi over 2 for every n, okay? And this is equal to 1. So with one sequence we obtain the limit 1, with another sequence we obtain the limit 0, okay? That means that the function, the original function, doesn't have a limit when x goes to 0, okay? So the limit does not exist, okay? And we know that again because the definition of the limit asks us to prove it for every single sequence, okay? Now, as you may be thinking, checking that this limit, any limit exists for every possible sequence may be kind of a pain in some cases. And so for this reason we have another definition which is similar to the definition we saw for limits of sequences, but it's kind of more abstract, right? So it's what we call the epsilon delta definition, okay? And so we say that the limit of a function f defined in the domain A with values in the real line when x approaches A is L if for every epsilon greater than 0 there is a delta greater than 0 as well, such that the difference between the value of the function and my limit is smaller than epsilon whenever the difference between the point x and the value of that we want to approach is smaller than delta. Okay, this seems like a mouthful, but the idea is that suppose we have any function, okay, it doesn't matter, and we want to see what's the limit of the function here, right? Now we say this is going to be L, right? Now we say suppose we want this the value of our function to be in here, right? This is L plus epsilon, this is L minus epsilon, right? Now that the limit exists, you just say that if we want the value of the function to be in this interval, right, we can always find an interval, and this is x, right? Sorry, this is a. We can always find an interval around a, which is what it means, right? This is a plus a minus delta and a plus delta, right? We can always find an interval such that the mapping of the values here, right? This mapping, when you get here, is only going to be in this interval. So it's contained in this L minus epsilon, L plus epsilon. So that's what this means, right? For every epsilon that we think of, and we can make this epsilon smaller and smaller and smaller, right? This is kind of a big one in order for us to draw it. But you can make it smaller and smaller and smaller. If the function has a limit in this point x and it is this L, we will always be able to find an interval a minus delta, a plus delta, with delta as small as we need to be, so that the mapping from this interval into the function is going to be contained in this interval L minus epsilon, L plus epsilon. Okay.